Yeah. So, good afternoon, everyone. Welcome to one more lecture in the PEPS Industry Lecture Series at IIT Hyderabad. And today we have another eminent personality from industry who will be delivering a lecture about recent advancements in Indian power system operation and control. So, let me briefly begin by introducing the speaker, Mr. Fanishankar Chilukuri, and he holds a Master of Technology MTech degree in Electrical Power Systems from IIT Delhi, and he has 9 years of industry experience and is presently working as manager at National Load Dispatch Center (NLDC) and Grid Controller of India Limited. So I think this is a new name, right? Recently, the name changed to GCIL, Grid
Yeah, it
Controller.
was it was POSOCO earlier. Now it is Grid Controller of India Limited.
So, which is a National Power System Operator of India, and he's a senior member, IEEE member, and a member in SIGRI. And he's skilled in PSSC, GAMS, Python, MATLAB, Simulink. And he is also recipient of Power Grid IEEE India Council Award for Excellence in Young Engineer category. And coming to his work, and also briefly about today's talk. So he's the lead engineer in the team which completed automatic generation control (AGC), which you might learn in any power system textbook. That AGC. So it's a pilot project in India, and he managed an important role in introduction and setting up of AGC in the Indian power system in 2021-22, covering more than 64,000 megawatt capacity in India. So he played a lead role in conceptualization and in-house implementation of security constrained economic dispatch. Again, that is SCED. It's a pilot project again in Indian power system, which has been led to national savings of more than 20 billion rupees, or in familiar terms, it is 2,000 rupees crores. Okay, so since April 2019, so a lot of saving has been achieved by their team, and Mr. Fani Shankar is a key member in that. He has been instrumental in designing the in-house developed territory control dispatch software for Indian power system in 2020, and he has hands-on experience in modeling, simulation, and assessment of power system reliability and transfer capability. So, with that brief introduction, I will hand over the session to our today's speaker. So, please go ahead, sir.
Thank you, thank you, sir, for those kind words of introduction. You're all able to see my screen, right?
Yes, we are able to see the screen.
Okay,
So you
so
can maybe go to the presentation mode so that it will be better
uh, I have
visible.
already placed in presentation mode. Now, is it there? Uh,
Okay, in our screen we are only seeing the
okay,
slides part. Yeah.
uh, or else I'll do one thing. I'll share my entire screen so that this problem sometimes comes. I'll share my entire screen once more. Now, is it in presentation mode?
Yes, now we can see in the
Right,
presentation.
right. Okay. So today's topic, as Pradeep sir has pointed out, it is on some recent advancements in Indian power system. These are some of the recent implementations. When we say recent implementations in the last 10 years, okay, and these were theoretical concepts earlier, but these were applied practically to the Indian power system. These concepts which we are going to discuss today. Uh, we will cover briefly about Indian power system, some concepts, some basics, and then we will talk about the implementation of reserve regulation ancillary services, or RRAS, which is the tertiary response ancillary service in Indian power system. Then we will talk about the secondary response ancillary service, or automatic generation control implementation in Indian power system. We will talk also about security constrained economic dispatch implementation in Indian power system. So these are all topics on which I have worked firsthand. So I would be speaking from my experience on these, right? So if you have any questions, you can definitely interrupt me in the middle of my presentation also, and you can ask, because there would be some acronyms I would be using unintendedly. but it may not be clear to you, right? So you can definitely stop me and ask a little more explanation or any questions that pop into your mind. At the end of the presentation, also, we would have some question and answer session. So, with that background, just let us move on. Um, Generally, in any power system, these are the three important categories: generation, transmission, and distribution. Okay, so when we talk about Indian power system, we have to know the dimensions of the Indian power system because it is very huge. So it is important to understand the scale of implementation about which we are talking, so that we understand why there are some approximations, why there are some nuances, and what scale of implementation has to be thought in mind before conceptualizing any new idea. So the Indian power system has around 388 gigawatt installed capacity generation, more than 100 gigawatt renewables already, and around 2000 generating units are there, and the largest unit size is around 1000 megawatt. There is lot of EHV transmission, extra high voltage transmission, already built in the Indian power system. Lakhs of kilometers, 4,45,000 circuit kilometers built by different agencies in the Indian power system. More than 100 gigawatt inter-regional capacity. That means from one region to another region, 100 gigawatt flows very frequently. So, and there are 13 high voltage direct current transmission links, and 3 gigawatt of international exchanges are also done by Indian power system with the rest of the with other countries, neighboring countries, Bhutan, Bangladesh, Nepal, Myanmar. The Coming to the consumption side, we have around 200 gigawatt plus peak demand very frequently, and around more than 4 trillion watt hour. 4 terawatt hour is met daily, and we serve 3.2 million kilometers square, large size of the Indian power system, and a lot of people are involved in this, right? So. Uh, Indian power system is one of the largest and the most complex machines in the world. So you have to understand uh, this fact. Like we were talking, we are the largest synchronous grid. In this map, I'm showing you the top 20. Although it is called as Geo 15, there are 20 independent system operators in this, uh, or the grid operators. So uh, in this, we are the largest, almost the largest national synchronous grid. We are one grid, and there is no other grid like this. USA is very large, but there are several grids. It's not one grid. Similarly with Europe and China, and we are third in terms of electricity generation, consumption, installed generation capacity, and transmission capacity. We're also fourth in terms of wind and solar generation, fifth in terms of renewable energy, sixth in terms of hydro, and ninth in terms of pumped hydro installed capacity.
Uh, um, I have a question here.
Okay,
So there is this recent initiative, across the world, saying that one world, one grid.
right.
So what is your take on it, and
So,
whether it
right.
is like a good concept or
Yes, yes. It is definitely a good concept because one sun, one world, one grid. It's the motto, or it's one uh, project which the government has undertaken. um, when you increase the size of the any system, you can also harness the diversity in India itself. There are different regional grids, so, and each regional grid behavior is different, some people wake up early, somewhere there is a sunrise earlier, some people work late. So that kind of behavior we see in the Indian power system also. And because of these connections, one grid connection with the diverse regions or diverse countries, we can harness the diversity, and it is more economical. We can share the resources amongst all the participating countries or the participating grids, which is economical to all the power systems. It's a win-win to every country. Uh, just like if three students go to a hotel and order a pizza, or one student goes to Domino's and orders a pizza, which is more economical. Obviously, when three go together, it is more economical, right? It's the same concept here also. Uh,
Yeah.
Harnessing the natural resources, preserving the fossil fuels. So that's the idea.
So good that you have given a restaurant analogy and not a exam hall analogy.
Yeah. Okay, let's move ahead. Uh, this is from the this is an illustration inspired from Sally Hunt's book, Making Competition Work in Electricity. This is a very good book. Um I encourage all those who are interested in electricity markets and ancillary services and those kind of projects. So they read this book. And uh, coming to the Indian power system, there are the basic four pillars defined by Sally Hunter: scheduling and dispatch, congestion management, ancillary services, imbalance and deviations. Indian power system has all these four pillars already built in. When I say scheduling and dispatch, uh, we ask the generators or participating power plants uh, to dispatch this much of power. So dispatch say 400 megawatts of power or 700 megawatts of power, and they are scheduled before, so that they know a priori what they have to generate, so that they will accumulate so much resources, and accordingly so many units can be brought on bar, and the units are ready to deliver the required power, because in the real time always load plus losses is should be equal to the generation that is generated by all these resources. Otherwise frequency will not be 50 hertz. So how do we know how much to schedule all these generators? It is through forecasts. So we try to look in the long range, which is called 1 to 3 years resource planning, and we also look at the short term forecast, medium term forecast, and short term forecast. So in the day ahead forecast, we see how much would be the probably the demand tomorrow, and based on that there would be day ahead schedule or an R0 schedule that is given to all the power plants to generate. All this activity is regulated. It is regulated by CERC regulations, or the state. When it comes to the state sector power plants, it comes to the SERC regulations. Just like we have a prime minister and chief ministers, so there are CRC regulations and SERC regulations. So, and the guiding document is the Indian Electricity Grid Code. Okay, when we talk about scheduling and dispatch, what are the objectives for grid operation? We look at frequency control, voltage control. We try to maintain tie line flows. We also look at the stability of the system, so that in case of uh, any faults or outages, the stability of system is not hampered. We also look at the internal flows, reliability. Particularly, we look at n-1, sometimes n-2 on for special cases. When I say n minus 1, when one element is out, the system should still survive without the need for large scale changes in the plan. So, and there should not be any oscillations in the grid. There should not be any violations in the grid as such. So that is called as n minus 1. We always ensure that the system is n minus 1 compliant. And we also look at the economy. Whatever actions the system operator takes, they should be economical. That means uh, starting from the least cost resource to the highest cost resource, we schedule them like that. So if there is a 100 megawatt power plant which is very cheap, let's say it is at 2 rupees per kilowatt hour. If there is a 100 megawatt power plant at 5 rupees per kilowatt hour, obviously we would schedule the 2 rupees kilowatt hour power plant first, and the 5 rupees power plant next. So that is called as merit order scheduling, or it's one way of ensuring economy in the grid. Similarly, all the actions that we take, they also have an economy angle in them. And whatever actions we take, they should be sustainable also. It's not like today we did something and we survived, but at the end of the day, the cost passes on to the consumers, the distribution companies and the consumers. So the actions that we take should not lead to a burden on the consumers. So such kind of sustainability actions also we take. It should not lead to a lot of pollution. It should not lead to uh, uh, the disruption of lives of the people. So such kind of actions also we take, so that whatever we do is sustainable in the longer run. So after scheduling and dispatch takes place, we are ensuring that okay, the generation is equal to load plus losses, that we are ensuring. Uh, Suppose there is congestion. Congestion means suppose uh, there is a limit on a certain line and enough power cannot flow on that line which we desire. So that kind of situation is called as congestion. So there are two areas. We want to flow 100 megawatt of power from area 1 to area 2, but the limit, the power flow limit between area 1 to area 2 is only 80 megawatt. So we call there is a congestion between area 1 and area 2, and the power has to be reduced by 20 megawatt, so that uh, the system is reliable and stable. Okay, then we apply something called as congestion management. There are laid down rules for that also. So after doing this congestion management, we may have to reschedule also, right? Because this 20 megawatt has did not flow from area 1 to area 2, so we will increase 20 megawatt in area 2. So that is rescheduling. After we have done all this, even then in the real time, that means just uh, few seconds before, or during the exact time of the day, in the real time, there can be a deficit between load and generation. Then what to do, because these things are planned a priori. Then in the real time still we have to do frequency control and voltage control, and control the tile inflows, and maintain stability. So we deploy something called as ancillary services. That means ancillary means extra. So these are extra services apart from the planned ones. So this is the third pillar of market design. So this these ancillary services can be for frequency control, can be for voltage control, or can be for any of these objectives. Okay. Uh, uh, That means we might increase generation in area 2 in such a way that the congestion is alleviated in the real time. Suppose even though we have scheduled power between area 1 and area 2 is 80 megawatt, but in the real time the power flow is 90 megawatt because area 2 is drawing a lot of power. Then we increase generation in area 2 by 10 megawatt by deploying ancillary services, so that the flows are minimized. Okay, and uh, and frequency is restored. Even though we have planned earlier and we have deployed ancillary service in the real time also, still there would be some deviation in the real time. It is a part of power system. Always there would be some imbalances and deviations, and that those deviations are settled through a mechanism called as deviation settlement mechanism, or DSM. Uh, so these are the four pillars of market design. These are present in every grid. So these are present in this form in our grid, in Indian power system. If you talk about US grid also, these are present. Any grid, these are always there. So we will focus today a little bit on ancillary services on which I have worked, and those are the topics for today, right? RRAS and SRAS, or the which is called as AGC and TRS. So these are the classification of ancillary services. There can be frequency control ancillary services, voltage control ancillary services, black start ancillary services as per the Indian electricity grid code. In the frequency control ancillary services, also they are classified as three types: primary, secondary, and tertiary ancillary services. Primary frequency control is mandated by grid code. In the primary frequency control, what happens is the governors at the power plants, they locally sense the frequency and they try to adjust the uh, governor in such a way, the walls in such a way that the generation increases or decreases based on the local frequency sensing. So based on a predefined droop characteristic, the generator might produce more or less power. If there is low frequency, the generator would produce a little bit of more power. If there is high frequency, the generator will produce less power. Secondary frequency control is presently regulated through secondary reserve ancillary services, and it is deployed through automatic generation control. So this is automatic generation control. Primary is governor control. Secondary is automatic generation control, where we change the load set points of the generators. We have an exclusive set of slides on this topic, so we'll talk about that. Tertiary frequency control is expected to be market based very soon. Presently, it is regulated through Reserve Regulation Ancillary Services (RRAS). There are other ancillary services also, voltage control and black start. We will not discuss about them today, but they are local provisions through regulated mode. They are facilitated in the draft grid code 2022. There is a draft grid code which has recently been notified, which would come into force in the next year. And I would also encourage all those power systems students, particularly, and power electronics students also, to go through the draft grid code. I've given references at the end of each section, so you can all click those links and read those resources. Okay. Uh,
I have one question here regarding this
okay.
ancillary services.
Okay.
So, coming to this tertiary service, can we consider, ABT as availability based tariff as one of the means
Uh,
of
no,
tertiary?
this in this the four pillars, tertiary comes here in the ancillary services. Okay, availability based tariff has been rechristened as unscheduled interchange in the later years, and it
Okay,
has been rechristened as deviation settlement mechanism in the later years. Okay, so
okay,
it comes as the fourth pillar of market design. It comes here. It is in the very real time, almost it's post facto. Okay.
okay.
Yeah.
And one more question is, the free governor mode operation.
Okay.
So I lost touch of this topic in a few years back. But
Okay.
earlier, I know that there is no free governor mode operation.
Right.
Right now, what is the status?
Right now, also there is no free governor mode of operation. It is a restricted governor mode of operation, or
Okay.
RGMO. It comes as primary frequency control.
So this AGC also that is
AGC,
AGC is something different. Yeah.
AGC is different. In AGC, we do not control the governor. We control the load set point of the generator. Okay.
Oh, okay. Okay.
So we automatically control load set point of the generator every 4 seconds from the control room from New Delhi to all the stations.
Okay.
So
Interesting. Yeah.
right. So we have set of slides on that. You will get to know that also.
Sure.
So this is some general gyan, but nevertheless, it would be useful for the students who are trying to implement something in their projects or in the Indian power system. Okay, so when we talk about the end-to-end implementation aspects, we have to look at different a stream of um, uh, a stream of applications before we conceptualize some idea. That, for example, when we have an idea, those ideas should be in line with Indian market structure, Electricity Act, grid code, uh, uh, and so on. So they should not be deviant from the existing setup, and they should not be big bang ideas, because such kind of ideas usually do not get implemented. They are good on paper, but they do not get implemented because power system has a lot of inertia. There is a lot of investment already sunk in, so you cannot change some things overnight. Uh, we should recall Steve Jobs, who said ideas are worth nothing unless executed. They are just multiplier. Execution is worth millions. So, uh, when we want to implement something, we should also know what software we want to use, what hardware is needed. Such kind of things also have to be thought through. Similarly, stakeholder satisfaction is also important. Those who are part of are the beneficiaries of the project that we are implementing, they should also get satisfied ultimately. So whatever we implement, that should be transparent and simple in power system. Similarly, um, scheduling is one big aspect in power systems. So there should be good software and good communication, very clear line of communication between the project executing agency uh, uh, and the devices or and the second set of project executors. Uh, Everything that are served through uh, served through the project, they should be metered because ultimately all this electricity should be clearly metered through energy meters, SCADA, etc. And there should be accounting of this also. Nothing is free, right? So all this electricity entails a cost. Somewhere coal has to be burnt, water has to be flown, somewhere there would be investment for solar panels. So they have to be paid back. So that's why accounting is also important, fast and foolproof accounting. And ultimately, all those who have contributed to the services, they have to be paid for. Uh, in India, there are different pools, national pool. Some special pools are created. So some funds are collected from the states and discoms, and they are distributed back to those who are offering the services. And we use a web-based scheduling software. We have some in-house customized all softwares, and we procure also some softwares from outside. We do public consultations um, frequently, and we have main check and standby meters in place, and we um, the accounting and settlement, because they involve money, they are regulatory backed. There is a central electricity regulatory authority, so we get a stamp from them. Okay, this method is foolproof, like that. For that, we have to convince them also by showing them the audit trail. This is the frequency control continuum in India. So after any disturbance, different frequency control actions come into picture so that we restore the frequency to 50 hertz. All the frequency control mechanisms, they are equally important. For example, if there is any generation loss in the system, sudden generation loss in the system, first frequency control action that comes into the picture is the inertial response, where all the rotating loads and all the rotating turbines, they provide power through rate of change of the kinetic energy, and there would be decline in frequency. This decline in frequency would be sensed by the governors locally, and the primary frequency control kicks in, and the primary frequency control would open the valves of the governor, and the stored enthalpy in the steam turbines that would be extracted, and uh, they provide the power to cover the deficit between load and generation. Then this is local, right? Then secondary frequency control kicks in. This is automatic generation control, and every 4 seconds signals are sent from the control room to all the generators to increase or decrease frequency. Because we are talking about a generation loss event, obviously we have to increase generation. And there is a tertiary frequency control also, which is manually changing load set points. In secondary frequency control, the load set points are changed automatically. In tertiary frequency control, uh, the load set points are changed manually. Okay, and discipline by all the stakeholders, portfolio management is important. All the states and the discoms, they have to forecast the demand, renewables, weather, and they have to come up with a balanced portfolio so that the generation that they are scheduling is equal to the demand. And we also look at the economy part. We commit those units, those many which are needed, ensuring reliability, and we do an economic dispatch of all those units which are committed. There are power markets and ancillary services also to bring more economy into the grid and to cover the last mile deficit between load and generation. These are some further readings for you. I have given links. You can click on these and just go through. The last one is the draft Indian Electricity Grid Code, uh, and uh, there is an explanatory memorandum also. You go through this. This is the first section. We have next we jump to the reserve regulation ancillary services or tertiary reserve ancillary service. Both are same. Earlier it was called reserve regulation ancillary services. Right now this is going to be market based, where the generators can bid in the market that we will offer 100 megawatt at 5 rupees, 200 megawatt at 10 rupees, like that they can bid in the market. That is called as tertiary reserve ancillary services. Earlier there used to be fixed cost. Um, uh, 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 an accepted cost for all these generators, and based on that they were dispatched. So how what the system operator thinks, what are the cues for the system operator to dispatch RRS is that the system operator looks at the weather forecast, load forecast, outages of the transmission lines, generating units, if there is an anticipated congestion, what is the reserve status. We look at SCADA visualization in real time. We monitor renewals and the area control error. You would have heard about the system area control error. We will talk about this. And um, this when I say reserves, there are two kinds of reserves. One is the normal reserve, the difference between P max and the P schedule. That is the reserve, right? What is the maximum a generator can generate, and what is the present operating point of that generator? The difference is the headroom which is available for the generator to generate. That is up reserve. Similarly, there is a down reserve, the present operating point minus the minimum till which the power plant can generate, that is down reserve. So we monitor both up and down reserves. But if we take the ramp rate of that generator also into consideration, that reserve is called as ramp constrained reserve. So uh, if we take a 15-minute ramp rate of that generator, then the reserve would be lower than the total reserve, because in 15 minutes we can dispatch only maybe one third or one fourth of the total available reserve. Typically, thermal power plants have 1% per minute ramp rate. That means if a 500 megawatt unit, it can only move at 5 megawatt per minute ramp rate. In that means in 5 minutes it can increase its generation by only 25 megawatt, like that. Okay. So system operator looks at,
Sir, I have
yes,
one doubt here. So
yes.
that negative side, what is it? I could not understand how
Uh,
spinning reserve can be negative.
the it is not negative, it is down spinning reserve.
Okay,
For for mathematical purposes or graphical purposes we denote it negative, but it is down spinning reserve. Down means how much.
understood.
Yes, yes,
From the operating point, how much reduction you can do?
reduction is possible, right? That's So the system operator has an interface like this. So I was part of this development team. So in this, we can apply uh, the system operator can apply the ancillary service, the or and about top up of increase or decrease in generation. So because of, see here, there is a reason, right? Because of decrease in wind generation, the system operator has applied 2000 megawatt. Because of increase in solar generation, the system operator has applied 1000 megawatt down regulation here. So we apply up and down regulation based on the short term forecasts or the operating conditions, and usually 30 minutes before these entries are made. So in the reserve, as a part of reserve regulation ancillary service, and we click this apply RRS button. So all the generators where there is reserve, all these generators would be either ramped up by 2000 megawatt, 1000 megawatt, ramped down by 2000 megawatt, 1000 megawatt, like that. Okay. And this is the broad architecture which we have used. Uh, uh, we have a user interface which talks with the core engine. This was built in GAM software, and it talks with the SCD engine also. It provides some inputs to this, and there is an application program interface which talks with the scheduling software of the web-based scheduling software at the RLDCs. And this software also has some database and which produces accounts, and we have built in some user interface also in this. And we to save time we mimic insertion of this RS dispatch into WBS. This nitty gritty. So broad mathematical model is like this. Um,
So once the that schedule is published in the website,
right.
so the RLDC scheduling software receives it, right? As
Yes, correct. That is
so,
right.
how it is implemented again? RLDC intern has to uh, communicate to
See,
the generator, right?
this RLDC scheduling software is also seamlessly interfaced with all the power plants IT system. So
Okay.
power plants get to know in their IT system what is the schedule at that point of time, or what is the schedule for them in the next 1 hour or next 2 hours also. So based on that, the power plant prepares and it generates. So
Okay.
they
Here,
look at the
what I am trying to understand is, right from NLDC up to the machine.
yeah, right.
I think at least in the last, the final, near generator, there
Right.
is a human operator involved, right?
Yes, yes, there is a human operator involved. For
Okay.
example, the
But only
uh,
at the in the generation plant there.
right. For example, this power plant, MPL, Python Power Limited,
Okay.
the person sitting at the power plant looks at this dashboard finally. Okay.
Okay.
There are different components in his schedule. Some he has traded in power exchanges. He has some long-term contracts. He has traded in the real-time market. There is this component RRAS. So this also gets inserted into the schedule. Okay, and the power plant has to follow the net schedule, including all these components. So this value he picks up. So 984. That 984 would be the load set point of that particular generator MPN. So the operator there enters 984 in his digital control system, and 984 is generated by the power plant.
Okay. So
Okay.
this new column has been added.
Yes, this new column has been added because of RRAS. Yes.
Okay. Okay.
Similarly, for in the SCD, which we are going to talk, also there is one new column for SCD.
So, at the time of, I'm sorry, I'm asking more
Ah,
questions.
no
So,
problem. This is what we require, because otherwise I will not understand whether you're
at the time of introduction, you mentioned that like almost like 20 billion rupees have been saved.
right.
So, how that this relate, this scheduling
Yes,
relate to
yes.
that savings?
So yeah, we will talk about that when we talk about SCD. But
Okay.
briefly, I'll tell you because you have asked the question. It would be like this. There are several plants which are scheduled by the. We have a decentralized form of scheduling. Okay, there are several central sector power plants in India, and all the states have entitlements in those central sector power plants. So, and these entitlements are because of long-term power procurement strategies by the distribution companies of the states. For example, Telangana discoms, they have some strategy. They will procure in, let's say, Ramagundam, some in Sholapur. Uh, so, like that, they will procure this much megawatts in bidding process. But in the real time, and they can go and enter into bilateral contracts. Also, they can buy and sell power in dead and real time markets. But what happens is, in the real time, we see that when we look at the all India picture, there are some relatively costlier power plants which are scheduled, and relatively cheaper power plant where reserve is left. So this SCD mechanism, what it does is it increases power in those cheaper power plants subject to some constraints, and it decreases power in certain power plants subject to constraints. For example, I have an example here. So suppose we have three generators A, B, C, and we have three states X, Y, Z. So and this states X, Y, Z have stakes, the state X, let us say, has stakes in all these three generators A, B, C by 1000, 2000, 1000 megawatt. State Y also has stakes in A, B, C, and Z has stakes in A, B, C like this. And the cost of A is 5, cost of B is 6, and cost of C is 7. So the total install capacity that is available is 15,000 megawatt. And these three states together, they want 12,000 megawatt. Each state wants 4,000 megawatt. So if we compute the production cost here, which is simply 4,000 into 5 plus 4,000 into 6 plus 4,000 into 7, it is 720 lakhs per hour. But if we apply a thin centralized optimization layer, um, we can see that this generator has still some reserve left, right? It is 5,000 megawatt capacity, but it is scheduled to only 4,000 megawatt. So we can increase generation by 1,000 megawatt. And in generator C, uh, we can decrease by 1,000 megawatt because we have increased here, we can decrease here. So we will decrease here by 1,000 megawatt. So this generator B gets paid from the national pool, and the generator C pays at the rate of its variable cost to the national pool because it is saving fuel here. So if we compute the cost now, the production cost 4,000 into 5 plus 5,000 into 6 plus 3,000 into 7, it's only 710 lakhs per hour. So there is saving of 10 lakhs per hour in this particular case. The states are still served at say the same amount, 4,000 megawatt, and the total is also still the same equality constraint, which is 12,000 megawatt. So the same example we have converted into mathematics and we have coded it, which is SED, of course, subject to the constraints.
Okay. But what about the long-term contracts or whatever of the generator C?
Yes, yes. So the long-term contracts remain unaltered. We are not entering into the contract structure at all. This SED takes place 30 minutes before dispatch. The contracts are already over by the day-ahead market time. Okay,
So
so
what I want to ask was this generator C, which was scheduled to 4,000
right,
megawatt. Out of
right,
that 4,000 megawatt, what if 3,500 are
okay,
under long-term open access or whatever?
right, right.
So
So there is
and
a
so that 5,500 megawatts issue will be there, right?
right. So there is a concept called as gate closure. Okay.
Okay.
So the concept of gate closure is that right now, 75 minutes before dispatch, the generator C, uh, the states lose their right to increase or decrease generation in generator C. So that is one concept which has been brought indirectly in the Indian power system while implementing this SCD. Okay,
Okay.
because of uh, uh, the real-time market also, this was very well received by all the states also. So 75 minutes before, there is a thing called as gate closure, and I think I have placed one slide here. Yeah, I have one slide. um, there is a concept called as gate closure, and yes, so 75 minutes before scheduling the time of delivery period, um, um, all the states can change the schedules in the generators any number of times. In generator C, it can increase, decrease, anything it can do. But after 75 minutes, the real-time market auction begins. So all the generators, all the states lose their right to recall or schedule in the generators. After real-time market, there is RRAS, and after RRAS, we do SCED finally. Okay, is that clear, sir?
Yeah, yeah. So
Right.
this is very interesting. So
Yeah.
this SCED will run, how much time it will take to run the
Uh,
optimization that you
so
are,
it takes hardly 1 minute. It's less than 1 minute.
okay, but it covers like close to 60 gigawatts of
It
generation.
covers. It's very quick because the that's what, because of the scale of implementation, we have simplified some things, and it is linear programming. The
So
equations are all linear.
another good thing what I'm noticing is it's like a in-house developed thing, right?
Yes, yes, it is entirely
If
in-house
it
developed.
was if it was developed by either is one of these companies like GE, ABB and all, so that their cost will be more than the saving that they will achieve. So good that you have
Yeah, right. Uh,
developed the.
so
Uh,
right now we have a good IT team also. We have recruited so many people. The computer science, IT, we have those teams also with us. Together with together with the normal power system team, we work closely with them and we develop all
It is
these
a real
softwares.
world example of how this optimization, that is
Yes, yes,
even if it is linear programming, how
yes,
that
yes, yes,
optimization can save a lot of
yes,
money.
yes,
Uh,
yes, definitely.
Please continue, sir. Yeah, continue.
So this is the broad mathematical model for RRAS dispatch. So uh, in RRAS, our decision variable is how much we have to each generator has to generate, right? And under RRAS, our objective is to minimize the cost of RRAS dispatch. Like we were talking about the general guiding principles, we always try to do a least cost dispatch. So that's why we do this. And subject to constraints, like we try to satisfy the reserve requirement, maximum generation limit, minimum generation limit, ramp up limit, ramp down limit, and there are some unique constraints for Indian power system, like unidirectionality. Uh, we do not have enough time to go into the nitty gritties, but um, these are our constraints. And the timelines we have briefly talked about: 75 minutes before gate closure, 75 minutes before the time of delivery period, there is gate closure, and the generators lose the pop states lose their right to recall or change any generation in the generators. Then after RTM, real time market, we dispatch this ancillary services, and SCD is also done at that point of time to save time. And 30 minutes before the delivery period, the power plants get to know what is the schedule of that they have to generate in the teeth time or the uh, x xth time lock. So around 30 minutes before they get to know. The use cases of this SRAs, TRS are,
So again, the timing is also visible here in the previous
yeah,
slide.
right.
So T minus 35, you start the algorithm
Yes, yes,
and you
right.
get the result in 2 minutes.
2 minutes,
And
yes.
the solution arrived at T minus 33. Then by
Yes,
the
yes,
time it updates in the website, maybe
exactly.
it will take about 5 minutes to update in the website.
Exactly, exactly.
So T
That's
minus 28. And the 28 minutes, the generators will have to,
time for
the
preparation.
column gets updated in 2 times. Sir.
Right, right. Excellent, sir. That's the correct understanding. Yeah. So uh, this is all India net demand in the purple, which I am showing. I hope the color is same for you. And because of the all India, looking at the all India net demand and looking at several other factors, this was the RS dispatch on festival day. Uh, on This was on Diwali day in November in 2021. So RRS up was given to support the morning and evening peak because there is ramping of demand here. And because of low demand during the high solar periods, RRS down was given. So you can see that we are allowing more solar to penetrate by decreasing the thermal generation. RRS down is given to the thermal generators. This uh, and uh, we also ensure that technical minimum also sometimes in some generators, so that because we need that ramping capability in the evening to support the peak. So that's why we keep some generators on bar so that we ramp quickly in the evening. So those are that is some use of RRAs. Similarly, during cyclone Taukte, it's an extremely severe cyclonic storm. There was low demand, and after the landfall, there was high wind, obviously. So, and we have applied regulation down, looking at the demand forecast error. The demand forecast error was 4,000 megawatt minus. So, obviously, we then applied RRAS down instruction in all the thermal generators, and we decreased generation by around 4,000 megawatt to compensate for the forecast error, because we were not expecting so much high wind. And to save the coal, and to uh, ensure the penetration of renewables, we applied RS down. So these are the through this we achieve reliability also, economy also, we maintain frequency. So these are some use cases. For everything, end of everything, there should be accounting and settlement. Those who provide regulation up, they will be they are being given at present 50 paisa per kilowatt hour apart from their variable costs. For those who are providing regulation down, they are being given 25% of the variable cost as markup, which is almost 50 paisa per kilowatt hour again. And they have to refund their variable charges to DSM pool, because they have saved their coal, right? They have not burned their coal, so they have to refund that amount. So uh, right now, these numbers would become market based once a market for RRAS comes up, which is called as TRAS. These are further readings. You go through these reports, you will get to know about more about these things. There is one recent CGRE paper also which we have published on this, 2022. The automatic generation control, or SRAS. Um, Earlier, automatic generation control was a pilot project. Now it has been formalized as an ancillary service, as secondary reserve ancillary service. From 5th December 2022, it will be formalized as SRAS. And right now, AGC is there on several power plants pan India. If you see the frequency plot earlier, it used to vary between 48.8 to 50.4 in April 2004. Um, but as time passed by, right now in 2022, we have a very nice almost 50 hertz average frequency. Similarly, this is one metric which we track. This also has sedimented down to zero. The ideal frequency variation index that we track is should be zero. And the maximum and minimum frequencies earlier used to vary widely between 48.4 to 50.51. But now the Indian grid frequency stays very close in between, um, a very narrow band, and our target is to bring it as close as possible to 50 hertz to ensure reliability of the grid. Okay. For this has been possible because of several interventions. We have talked about frequency control continuum, right? So because of different interventions, right from ABT, after that DSM, RRAS, AGC, all these have contributed. Good forecasting, portfolio management, and all that. So after any contingency, sudden generation loss, first the inertial response will help in the slowing down of the initial rate of change of frequency. And after that, the primary frequency response brings the frequency to a quasi-steady state frequency to governor action. And AGC then picks up to replenish the primary frequency control so that we are ready for the next contingency. If AGC or the secondary frequency control is not there, then if there is any contingency at this point of time, the governors uh, will not be charged fully. So they cannot contribute to any other contingency that might happen. So such kind of situation might lead to uh, reliability issues. Then tertiary frequency control replenish the secondary frequency control, and if needed, there would be generation rescheduling also in the next 1 hour. Okay. One important metric when we talk about AGC is area control error, where we look at the difference between IA minus IS and FA minus FS. So IA means net interchange actual minus the scheduled net interchange. FA is actual frequency 50, actual frequency minus scheduled frequency is 50 hertz. So if actual frequency is 50 hertz and IA is equal to IS, then offset is for compensating errors such as measurement error. Its default value is 0. So if these three terms are 0, AS would be 0. The objective of AGC is to drive this area control error towards 0. For AGC, we treat each region of India as a balancing area, or a control area. Okay. So when AS is positive, that means this area is in surplus and its internal generation has to back down. Case is negative means it's the area is in deficit and the internal generation has to increase. So briefly, what is automatic generation control? This is an automatic supplementary control mechanism 24 by 7 to control frequency and tie line flows. Several signals are exchanged between the NLDC and the power plant every 4 seconds. AGC will help replenish the exhausted primary reserves so that we are ready for the next contingency. It's an efficient and automatic frequency control during high RE periods. More than 67 power plants are there under AGC as of now, with 65 gigawatt capacity. It is aimed to improve the reliability of the power system. So we have so many coal gas hydro plants under AGC. From Delhi, all these plants are controlled from the National Dispatch Center. From here, we control NTPL, which is around 2,760 kilometers far away. We control Loktak power plant in northeastern region, which is around 2,500 kilometers far away. So you understand that robust communication infrastructure is important for AGC. Already there are fiber optic cables laid from Delhi to NTPL, Delhi to Loktak. That is why we are able to control these power plants. Okay, and this AGC at present does 1,500 to 2,000 megawatt of generation up and down pan India continuously. Um, we source all the data from the RLDCs, the tile and flows and frequency data through router come firewall. We give the AGC set point or IEC 104 communication protocol. So what I urge all the students is that you also try to read up on communication protocols and all, because the next generation of power systems is going to be fully based on IT and communication. So those are reading classical power systems, that is needed, but you also have to read up on the latest protocols, particularly IEC 104, the newer smart grid protocols and all that. Okay. Through optical fiber ground wire network, the signal reaches the nearest communication node, and we have fiber optic cables laid till the control room of the unit, and there is a remote terminal unit dedicated for AGC. That remote terminal unit is wired with the digital control system of the power plant. So this digital control system of the power plant exchanges a lot of signals with the NLDC software every 4 seconds, and the NLDC software provides signals to the DCS every 4 seconds. So there are a lot of stakeholders involved. Communication is provided by the central transmission utility. AGC generators are the SRAS providers. We have a industry grade software for AGC. We have customized it for Indian requirements. The regulator provides the regulations. They have admitted AGC as an ancillary service. There are performance incentives based on good performance. These power plants would be given some incentive. And the regional power committees, they do the accounting, performance and settlement. We exchange all these signals with the power plants, and the main signal that we send from an NLDC AGC is the planned AGC set point, how much that power plant has to generate. We exchange digital and analog signals through the optical fiber ground wire OPGW cables laid by power grid and all the transmission providers. This is our control room on 15th August 2021 night shift. There was little monitoring on this, but still AGC did up and down. The green is the AGC delta P, yellow is the frequency. Whenever the frequency is down, AGC increased generation. Whenever the frequency is high, AGC decreased generation. So it is a 24 by 7 automatic control. What AGC does is it changes the load set point of the generators. Uh, it uh, the RGMO, or the primary frequency response, it gives inputs to the governor, but AGC changes the load set point of the generators. This is a typical day operation. I think we are running out of time, but I'll just quickly go through the slides. It's a typical day operation where we have 24 by 7 automatic control. AGC enables continuous up and down cycling, and it respects power plant constraints like maximum, minimum, and ramp rate, obviously. Correct. Otherwise, power plants cannot perform as we need. And you can see that during high solar periods, AGC gave here 1500 down instruction continuously. This is one signal to the RRAS dispatch, manual RRAS dispatch, that okay, there is a 1500 megawatt offset. So RRAS, if you punch 1500, this secondary frequency control will be relieved, and it can do up and down cycling again. So like that, it helps in saving coal also in this way. During contingencies also, we have seen excellent performance during contingencies like generation loss or load loss. AGC quickly reacts by changing the load set point of the generators under remote, and it helps in driving area controller towards zero. So from 0 to 800 within 8 minutes. So around with 100 megawatt per minute ramp rate. Typically, a thermal power plant gives, like I told, 5 to 10 megawatt per minute ramp rate. But AGC has so many generators under its fold, so its ramp rate is much quicker. The power of unity, because there are 10, 15 generators at a time available for dispatch. So we get 100 to 200 megawatt per minute ramp rate. Similarly, there was a 1500 megawatt load loss. An arc furnace tripped somewhere in Madhya Pradesh, and a quickly 300 megawatt ramp down was issued by AGC, like that. So while AGC controls the power plant, the typical power plant is something like this. Typical power plant response. The black is the AGC set point. Red is the actual megawatt. So eh, uh, when the power plant is under remote, the always red should follow black, the AGC set point, to a large extent. While doing so, see, all these instructions are in ramps. So because we honor the ramp rate and we want to do a smooth control of generation instead of steps, power system always does ramp limited control. Okay. Like I said, we honor the ramp rate of the power plant. Hydro power plants are also there. Hydro power plants under AGC, they have Francis turbines in India. Several hydro power plants. The Francis turbines have forbidden zones. They are also called as vibratory zones or high cavitation zones. They are fed into the AGC software, those zones, and sustained operation is prohibited in that forbidden zone. And we facilitate quick transition through that forbidden zone. Uh, for this area controller, we do not use the raw haze, but we smoothen it. We use something called a smoothened haze. We use a EMA filter and a PID filter as of now to smoothen this haze, and we tune this PID controller using simulations. I've given some links you can read up. AGC uses smooth haze, which is the output of PID controller. Tuning PID controller is typically done using combination of simulations and engineering judgment. uh, we have tried several combinations. If you use do ideal tuning, it is nice, but if you use a large integration time, obviously the response would be sluggish. If you have a small integration time, there can be chance of overshoots. So there is one very good book by Hassan Bevrani. He's an Iranian Japanese. He has written exclusively one book on intelligent automatic generation control, where he has applied intelligent techniques on AGC, and it's a unique book. Uh, those who are interested in AGC, they can read. Okay. So, how to allocate this smooth end area controller among generators? We use something called as custom participation factor, which is suggested by CERC, agreed by CERC. And for up regulation, the division is in proportion to the ramp rate and inversely proportional to the cost. For down regulation, it is proportional to the ramp rate and cost. For example, for issuing up regulation, we issue up regulation to such a generator which is cheaper and which has a very high ramp rate. Vice versa for down. Like I told, for everything we need accounting and settlement. This is the how we do accounting and settlement. We pay energy charges and incentives to those generators. The incentive is in between 0 to 50 paisa, and based on performance. Okay. We look at performance using a scatter plot.
I have a question here.
Yeah,
Under this AGC, how much of the generation is there?
around 65 gigawatt, 65,000 megawatt is there around. It is
Okay.
wired, but all the 65,000 megawatt generation does not have reserves. Some of the pithead plants, they are already requisitioned by the states because of their long-term contracts. So there would
So,
not be any reserve in them. Yeah.
but you mentioned also the RRAS, right?
Yes.
So under that, it is lesser. I was expecting that AGC will have lesser participation.
No, both RRAS and AGC, they use whatever reserves that are left. Okay. For
Okay.
RRAS, in the latest market-based TRAs, there is a method for reserve procurement. You can procure reserves from the market. Okay,
Okay.
but in AGC, we are using only reserves on as is where is basis. If there is reserve left in that power plant, we use them, but we do not procure anything. There is no opportunity cost that is paid to the power plants because we
So,
are
the
not
way you
making
explained, this AGC is actually like there's no human intervention in it.
no
It's
human
more like a
intervention.
closed loop control,
Yeah, nothing.
but the volume may be less compared
Yes,
to
yes. The volume is less because as of now we are not procuring any reserve, and we also do a ramp limited dispatch, right? So that's why it takes time to build up a good volume.
So, but here the objective is to stabilize the frequency.
Yeah, right.
Whereas in RRAS, the objective is for the economic dispatch.
No, no. SCD is different. SCD is for economic dispatch.
Okay.
RRIs is also for frequency control. RRIs is for tertiary frequency control. Okay.
Oh, okay.
RRIs, the load set points are changed manually.
Okay.
So manual instructions are sent from NLC control room. So we punch, as I have shown in the
Yeah, yeah.
display, we punch there and those are added to the schedule. Here there is no scheduling in AGC. In AGC, this signal directly reaches the load set point.
Okay.
So from Delhi to Tuticorin, signal reaches and it enters the digital control system of the power plant, and the power plant will dance according to the tune. So it will increase and
So,
decrease the generation.
here also, like it is done at a national level, right?
Yes,
So
yes,
maybe there are like more than 100 generators receiving the
yes,
APC signal.
yes, yes, yes. Almost 100 at a time.
So what is the algorithm you use?
For AGC, like I told, uh, currently the controller is PID controller, which is industry grade.
Okay.
Typically industry softwares have PID controllers, both the power plant and at the
But the PID
NLC.
controller,
Yeah,
if I mean, you are working on the area control, area
yeah.
error. Right?
Area control error. Yes, yes.
So how do you convert the area control error output to
Ah,
individual generators?
right. So that is called as participation factor.
Oh, okay, okay.
So we use something called as custom participation factor, where we
So these are
divide
like
this amongst, yeah, where we
fixed
divide this,
constants which are updated regularly.
correct, correct. So we look at the ramp rate and variable cost, and based on the, if the power plant is very cheap and it has high ramp rate, give we start with that and we fill it.
Good. So here also you're looking at the cost.
Yes, yes. Every action that the system operator takes, we have to look at the cost because we have to ensure economy. That is our guiding principle, right? In the first slides, we have already talked about that.
So, but is it not better to consider, the proximity to the loss of generator, you know, that
No, that is not needed. See, frequency is a global parameter. It's not a local parameter. So that is why uh, proximity to the local loss is not needed. In fact, if we suppose, for example, Ramagundam power station, let us say Ramagundam 3 has tripped. Okay,
okay,
Ramagundam 1 and 2 are there. Let us say Ramagundam 1 and 2, there is reserve also, and they are of 5 rupees, 5 rupees per kilowatt hour. Uh, but there is one power plant in the northern region, Singrauli, which is only 2 rupees. Okay, so because Ramagundam 3 has tripped, whether you will increase generation in Ramagundam 1 and 2 or in Singrauli, that is the question that we face.
yeah.
The best thing is to increase in Singrauli because it is only 2 rupees per kilowatt hour if there is reserve in that power plant.
So, but what about,
So,
power oscillations and power swings,
Ah,
etc.?
so usually power oscillations do not come because we employ certain margin while declaring the available transfer capability limit.
Okay.
And right now, a lot of transmission is already built in Indian power system. So there is, unless there is congestion, there would be lesser chance of oscillations. Okay,
And also,
so
you're respecting the ramp rates and
we
all.
are already respecting the ramp rate. We are using a PID controller, which is tuned. So the response is very smooth. So the chance of oscillations is very, very low. Okay. And only in case of rate of change of frequency, the frequency movement is local. Otherwise, the Indian grid is one synchronous grid. So we harness the diversity that is there in Indian power system. To the extent possible, we operate in constant frequency mode. Sometimes when there is congestion, we operate in tie line bias mode also.
Okay.
So the bias which we take for the K delta F, the bias is based on the frequency response characteristic of that region. So here the BF which we have used, that is based on the frequency response characteristic. There's IEEE Task Force Report 2017 which says that this BF, the closest or the best optimal value for this BF is the frequency response characteristic. That means if there is suppose for example the southern region's frequency response characteristic is around 10,000 megawatt per hertz. So that means 1000 megawatt per zero point 0.1 hertz. So if you want to change uh, uh, the any zero point 0.1 hertz in an isolated southern region, then you have to change 10,000 megawatt of generation here, 1000 megawatt of generation here. Okay.
Yeah. So one on the similar topic, see the allowable variation in the frequency. So I believe in India, the compared to other countries, the band is slightly more.
Yes,
It used to be much more, but right now it.
the upcoming IAGC it gives 49.95 to 50.05 hertz band.
Okay, okay.
The
55 to
band is
55.
almost same in Europe and India. Actually, in India, this 49.95 to 50.05 is managed for around 80% of the time. Okay, because of the resource constraints that we have. But
Yeah.
in Europe, the band is the frequency lies within 49.95 to 50.05 for 100% of the time. So that is the main difference.
Okay.
Otherwise, the band is decently tight for all.
Yeah, yeah. It is now. Now we can speak in millihertz. Right now it is like
Yes,
100
yes,
millihertz.
yes. The
So
draft grid code also says that you always show third decimal for frequency,
okay, okay.
50.005 hertz, like that.
Oh,
You will mention.
okay. So in that case, the measures that you're like the subject of your today's talk, like recent advancements. So
Right,
how does these techniques, compare with the techniques followed, in other power systems,
right.
in
So,
US or in Europe?
right, that's one good question. See,
Hmm.
we are actually in some fronts we are doing better than other countries also. Some fronts, and because these recent advancements have been possible now because of several interventions that were taken earlier. Okay, so one main aspect of Indian power system is merging of all the synchronous grids. We have five regional grids, right? So all these five regional grids have been interconnected over a period of time, and I have also been able to see the matching of new grid, northeast west grid with the southern region grid. So right now India is one grid. So this is one very big strength for Indian power system, uh, which is not there in other countries. So we can harness the diversity and use the resources in a very economical manner within India. Okay.
Yeah.
First point is
So,
that.
I mean, for the benefit of viewers, so the first plot on the top left, the x-axis is in years actually. So starts
Yes,
from
yes.
2004 to 2022.
Right.
So over almost like 18
18
years.
years.
So over the 18 years, how the frequency variation has gradually, become more and more less, and finally it is very tightly maintained.
Right. So that you can see clearly here. And the second is the resource adequacy part. That means always you have to plan ahead 3 years, 5 years, so that there is no coal shortage. We have sufficient links. We have sufficient solar panels that are manufactured and deployed, sufficient windmills, sufficient projects that are commissioned to manage the demand that is rising in Indian power system. So then only we can maintain this frequency. Demand comes up if generation projects do not match that speed, then also there is problem. If generation projects are commissioned and demand doesn't come up, then also the generation projects are stranded and they go into losses. That is also one problem. So they have to match a speed, and with the gradual development that the overall India is seeing, that will reflect in all the parameters of the power system also. That is what we see, that power system is almost a reflection of the day-to-day activities which we undertake. For example, for having a very tight frequency, if we invest lot of resources, if we purchase 10 Tesla batteries and make frequency 50 hertz, what is the use? All the cost of all these 10 grid scale batteries would be passed on to the consumers, right? So it's not economical. So we don't undertake such kind of projects. So these are further readings on AGC. Okay. SCD we have talked about briefly, where uh, we have seen that there are different projects in India to harness the diversity in Indian power system. Uh, we increase power in some lower cost power plants and decrease power in the higher variable cost power plants wherever there is reserve. And we still serve all the state's demand, but we achieve savings in the last after gate closure. So all this happens after gate closure, the security question, economic dispatch. So we are not violating any the long-term contracts also, and also we are achieving economy to some extent. So our objective is to minimize pan-India variable cost, subject to meeting total requisition by the states from ISGS. So this is our equality constraint here. Similarly, we have to see the transmission constraints, ATC constraints, technical minimum of the plants, maximum, ramp rate, ramp up rate, and ramp down rate. So, because all these constraints and objective is linear, use linear programming. This is the information flow. We take data from generating stations and states through the web-based scheduling software. We pre-process the information. We run our optimization core engine in linear programming and post-process the information, both using general purpose programming languages. And we give back the information to the WBS, which is then passed on to the RLDCs and to the generating stations and states. The state schedule doesn't change. In RRAS also, the state schedule doesn't change in SCD also. Okay. Only the generating stations schedule changes. We are trying to meet the demand of the state. So here there is no change. Here there is change. This process runs every 15 minutes, every time now. In lower variable cost stations, the power is maximized wherever there is reserve. Here, the blue is the schedule of the power plants before SCD. Orange is the schedule of the power plants after SCD. So, and this is the maximum line. So, before SCD, there was a lot of unused reserve here in the lower variable cost power plant. So, this was maximized and commensurate. Uh, amount is decreased in the costlier power plants, which is this is in southern region, this is in eastern region, because there are coal mines nearby. The variable cost is lesser here, but here it is slightly costly. It's not a pithead plant. So here blue is the schedule by the states, but SCD has brought it down to technical minimum value, and it is ramped only when needed. And thereby we achieved this 2 crores per day savings. And this also passes on to the consumers. See, 2 paisa per kilowatt hour reduction in average variable cost has been achieved because of SCD mechanism. It amounts to something. It's not very big number, but it's still decent. So the benefits are passed on like this. The national pool account maintained by SCD. Generators are paid up for the increment in variable charges, and wherever there is decrement, the generator pays at the rate of its variable charges. And for heat rate compensation, because generators lose efficiency when they operate at a lower value, they are paid some compensation for backing down generation. So the net benefit will be the the amount that is paid by the decrementing generators minus the incrementing generators minus the heat rate compensation. This benefit is passed on to the discoms and to the generators 50-50%. These are the further readings on SCD. That's my presentation. Any questions, please? We have published a lot of literature reports and some SIGRE papers, some IEEE papers also in some conferences. Please go through them. I've given links.
Hello.
Yes.
Sir, I had two questions. Actually, for your kind information, I am not a student. I'm just practicing electrical engineer in a
Okay.
400 kV substation.
Okay.
Like, I just want, in the big, one is a national one, like, regarding this, recently we have been associated with the solar plants very much, right? We are more dependent on solar power.
Okay. Please go ahead. I can hear you.
Yeah, I thought we got disconnected. Like,
Uh-huh.
how as a national grid operator, last year also I was going through the POSOCO website. On the solar eclipse day, you were working on a lot of things, and like it was a, I don't know whether nightmare is the right word or not. Like you were working more on solar eclipse day for this, and like how to see that on a national grid when we lose a renewable source like a solar plant.
Right, right. So yeah, so we also publish reports on POSOCO
How
website
to
regarding
see
this.
in a picture with this
Right,
kind of stuff
right, right.
in
So
operation.
like I told, one of the very important activities that POSOCO undertakes is scheduling and dispatch, right? So for that, we have a lot of forecasts. We have weather forecasts, RE forecasts, load forecasts, and everything, both from external agencies, and we have our in-house forecasting platforms also. So we take cues from all that, and sometimes we publish reports before the eclipse also, after the eclipse also, on how to handle this eclipse. We have contingency plans drawn up. Suppose if we lose 2000 or 3000 megawatt generation at a time, then what to do? For example, in the recently happened lunar eclipse also, in the recently happened solar eclipse, there was a lot of demand variation, unexpected demand variation, and on that also we tried to manage, but uh, our forecast went haywire, to be frank. So because people go for holy baths after eclipse, particularly in the northern region and the eastern region. Ganga belt is very particular about that. So we do not know how the load responds at that time. And because of the increasing right now, because of the change of weather also, geysers got switched on at some places, and the demand was slightly unexpected for us. So these
Yeah,
kind of
I
things
heard
happen.
about those rice cookers in Kerala, something like that. All of a sudden at 7:50 or 8 a.m.
Yeah, so the demand is very uncertain. But on the renewable monitoring side, luckily we have a lot of forecast service providers, and we have our in-house forecasts also. We look at those RE and demand forecasts, and we plan accordingly a priori. After that, we improve on whatever we have learned. We publish those learnings as reports, and they are available on Postgres website. Those who are interested, they should definitely look at it.
Yeah, and the second one, uh, in the beginning, Professor Pradeep was asking a question about one grid, one world, one grid, right?
Right,
Right now we are on one India, one grid. Okay, that's fine.
right.
Like I'm presuming that okay, I lay some power cables in the Pacific and connect east and west. Okay, uh,
It,
and also the some frequency I'll add some HVDC links or whatever. Um, while going for an islanding or something like that on a national grid as a grid operator on a national level, is it possible for us in near future to go for international grid control?
yeah, yes, yes. There would be international grid control stations also. In fact, the we are in a very tricky situation. We are also simultaneously talking about distributed system operators, where we have small system operators instead of the larger one. Apart from the larger ones, we are also talking about this international control centers also. Both are needed. Both will come because we are heading towards globalization, and already we are not one India one grid. We are already connected very tightly with Bhutan
Yeah,
supplies around 3000 megawatt of hydropower to India during its peak, and 70% of the GDP of Bhutan is based on this power supply agreements.
hmm,
So we are very tightly coupled with Bhutan. We are decently coupled with Bangladesh, uh, and we are increasing connections with Myanmar and Nepal also. So uh,
regarding cyber security, recently in Telangana also some in SCADA and SAS we were told that to disable all the ports and all. Can it be taken care when we have one grid internationally?
yes, yes. See, all these come hand in hand. Like I told, we have to look at all the aspects. Cyber security also, there are separate cells that are formed in all the RLDCs and LDC. There are separate control rooms working on cyber security alone, security operations centers. And right now, the governments, both central and state governments, they are very keen on this. So resources are also being allocated to handle cybersecurity. We, as such, India is to say per se very good at these kind of softwares and cyber aspects. So hopefully, there is no dearth of skill or and with the government push, uh, we will lead this arena in no time.
Thank you.
Yeah, we have time for maybe one more question from anybody else. Yeah, so if there are no further questions, I would like to maybe conclude the session by formally thanking today's our speaker. And this is a very good example of the how we are developing technologies on our own, like Atmanirbhar Bharat kind of technologies. So by doing that, we are able to achieve much larger savings by with less investment. So it's a very good example. And thanks for sharing your knowledge. So we will be definitely in touch with you in case any future work comes on this. Yeah. Thank you.
Thank you.
Thank you.
Thank you, sir. Thank you all the students for patiently listening. Signing off.